Good morning, my dear students. So this is our 4th class. So in this class we are going to see about Breton cycle. So that is Breton cycle about regeneration. What is the effect of regeneration, then what is the effect of reheating, and then intercooling, and the problems related to all this. So about Breton cycle and regeneration, reheating, and intercooling. Okay, so in this class we are going to see, so what are the problems that can be given for this GATE 2021. The way in which we can easily express, or we can easily apply the correct answer for the problems that are given for this GATE 2021. Okay, and moreover, so here in this lecture, so we are going to see about the basic functions of this Breton cycle, and then about all this and the formulas, what are the formulas which are related to this Breton cycle. Okay, so and so far we have seen about this in the previous class we have seen about this Rankine cycle, and in this class we are going to see about Breton cycle. So in this class we are going to see about this Breton cycle, and you can see that so Breton cycle it is a gas turbine which is also called as a combustion turbine. So it is a type of internal combustion engine. So it has an upstream rotating compressor which is coupled to a downstream turbine. So and a combustion chamber in between them. So the basic operation of this gas turbine is similar to steam power plant. So except that air is used instead of water. Okay, so these turbines are sometimes it is referred to as turbine engines. So these gas turbines are sometimes referred to as turbine engines. Such engines, they usually feature an inlet, fan, compressor, combustor and nozzle in addition to one or more turbines. Okay, so a gas turbine power plant. So for power generation, so for with the low capital cost and high reliability, and it is flexibility in operation. So because of its low weight per unit power, gas turbine is exclusively used to drive aviation systems. So for all kind of aircrafts. So this is an important term. So you have to remember. So why this gas turbine power plants are used in this aviation systems, especially in all kind of aircrafts. It is because of its low weight per unit power. So we are using this for this kind of for this aircrafts. Okay, right. So the next is closed cycle and open cycle. So this is classified. So one is open cycle, that is more common, where the combustion products after doing the work in the turbine are exhausted to atmosphere. So when in case of a closed cycle turbine, that is closed cycle plant, the working fluid, so that is it may be air, helium, argon, carbon dioxide and so on, is externally heated and it is cooled, and then it operates as a closed cycle. Okay, so when it is externally heated means by means of burning a fuel or with the help of some nuclear reactors. Okay, so when you go for the analysis of this turbine power plant, so we can see that heat supplied is Q1 is MACP in T3 into T3 minus T2. So this is otherwise called as a constant pressure cycle also, or otherwise called Joule cycle. So you can see that the heat addition takes place here at a constant pressure. So heat supplied Q1 is equal to MACP into T3 minus. These are the formulas that are used. And one thing is, apart from the other ratios, here you have pressure ratios. So far you are studying different types of ratios. So but here you are going to study about the pressure ratio. That is RP is equal to P2 by P1. So the efficiency of the cycle, that is equal to 1 minus 1 by Rp whole power gamma minus 1 by gamma. So this can also be written as 1 minus T1 by T4 whole power gamma by whole power, so gamma minus 1 by gamma. So this Rp max is equal to T3 by T1, so into gamma by, that is power gamma by gamma minus 1. So these are the formulas which you are going to use in the problems. Okay, so this is the maximum temperature and this one is the minimum temperature. So you may get in the problem as the maximum temperature is this much and minimum temperature is this much, and you have to use and you can find the value of the maximum pressure ratio. Okay, suppose if you want to find the optimum pressure ratio, so this RP optimum will be equal to this RP max power 1 by 2. So this power 1 by 2, it becomes gamma by 2 into gamma minus 1 in this formula. So then the net work is equal to MA into Cp into T max power 1 by 2 minus T minimum power 1 by 2 inside the bracket. So it is the square. Okay. So these are the formulas which we have. So apart from this, you have some other formulas also. So you can see all those in the problems. Okay. So if compressor and turbine efficiencies, if you are considering the compressor and the turbine efficiencies, so you will get this TS diagram like this. So this is ideal and this one is actual, and similarly here this is ideal and this is actual. So and this work is the compressor work. So when you consider T2 and T1, so you can get the compressor work, and when you consider this 3 and 4, T3 and T4, this is turbine work. Okay, so the turbine work will be the change in temperature, that is T3 and T4, and for the compressor it will be the change in temperature of T2 and T1. Okay, so efficiency, when you want to find the efficiency, so this is work done, that is output. It is nothing but the output by input. The output is nothing but the amount of work done, that is the net work done. So what is the net work done? It is the W net will be equal to, so WT minus WC. So that is divided by what is the amount of the heat energy that is supplied. So what is the amount of heat energy that is supplied? So eta will be equal to this W net by Qs, Wt by minus Wc divided by Qs. So apart from this, when you go for, when you consider these efficiencies, that is turbine and compressor efficiencies, so the formula for this optimum pressure ratio has to be given like this: eta C into eta T power inside the bracket T3 by T1 power gamma by gamma minus 1. Okay, so when you consider this turbine efficiency, so you have to multiply this compressor and this turbine efficiencies with this RP optimum. Okay, so the variation of efficiency, that is variation of cycle efficiency with RP. So you may get these kind of graphs in problems. So you have to know, so what happens when you draw a curve between efficiency and this pressure ratio and net work done and the pressure ratio. So you can get a curve like this. So when you go for, so as long as you improve this pressure ratio, the efficiency also increases. But at certain point, so it becomes the pressure ratio is maximum. Okay. So similarly here in case of net work done, so you will get the optimum work done and also the maximum pressure ratio, where you can see that the net work is very less at the maximum pressure ratio. You can see at optimum the net work done is maximum. Okay, so this is the variation in cycle efficiency. Here the work ratio is defined as the ratio of net work to the net work done in the turbine. Okay. So you will get questions related to this work ratio. So what is work ratio? It is the ratio of net work and the work done in the turbine. So work ratio WR will be equal to, so this net work W net divided by W, so work done in the turbine. So you have to know this formula. Okay, so based on this you will get problems for this. What is that variation of cycle ratio, cycle efficiency with the pressure ratio. So when you go for a problem, that is the maximum and minimum temperatures in gas turbine cycle are 1400 Kelvin and 280 Kelvin. So you have to draw the graph. So when you draw the graph, so you can see that the maximum and the minimum temperatures are given here 1, 2, 3 and 4. So the maximum temperature, that is T3. When you draw this TS, so T3 is 1400 and T1 is 280 Kelvin. So that compressor and the turbine efficiency are given to you. So eta C and eta T. So is 0. Compressor it is 0.85 and for turbine it is 0.9. So what is the optimum pressure ratio for maximum output condition? So you are going to assume this as the open cycle gas turbine. So the formula is given to you for optimum pressure ratio. Formula is given to you. So you know the maximum and the minimum temperature, you know the value of gamma, you know efficiencies. So directly you are going to substitute the values of this efficiency, that is 0.8, 0.85 and 0.9 into T max is given to you. So 1400 divided by 280, and even you substitute this, you can get the value as 10.46. So mostly in case of Brayton cycle, so you will get direct questions, mostly direct questions by substituting the formulas, or the formulas which are related based on the formula. So you have to choose the appropriate answers, and also based on the statements. So you may have different statements for regeneration, reheating and intercooling. So from that you have to choose the correct statement. Maybe all the statements may be wrong, right, or any one of the statement may be right. Okay, or one, two. If there are 4 statements, so maybe any one may be wrong. So each and every statement has to be carefully studied, and then you have to answer the question. Okay. So next is, so in an ideal air standard gas turbine cycle, the minimum and the maximum temperatures are given to you. The optimal pressure ratio for maximum work output will be similar to that. So our optimum is T maximum divided by T minimum, then gamma by 2 into the gamma minus 1. So that is the formula for this. So all these values are given to you. So you can easily get the value of RP optimum. So you can easily find the value by simply a single formula. So the next one is an air standard gas turbine cycle has a pressure ratio of 5, that is P2 by P1 is 5, and the inlet conditions are given to you. So inlet conditions P1 and T1 are given to you. The maximum temperature in the cycle is also given. So that is T3. So this is T3 is given to you. So convert T1, then P1. So this is P2 by P1. So all these data are given to you. So the air flow required for 110 kilowatt. So power is given. Okay, so power is given, then the air flow required for 110 kilowatt power output. So the air flow, you have to find the mass flow rate. So what is the mass flow rate for this? So the value of gamma and Cp are given to you. So among these answers you have to choose the appropriate one. So how you can work out this? So you can see here, so the TS diagram is here. So you can see, so power is the MA into net work done. So this same I told you, so you have to find the value of this mass. So MA has to be determined. So for that you know the value of power, but the net work done is not known to you. So how will you find the value of the net work done? So it is WT minus WC is nothing but the net work done. So WT, so from this you can find that is what is that, MCP into that is T3 minus T4, and here it is for compressor it is MCP into T2 minus T1. So this is compressor and this one is turbine. So you can easily find the values, but you have to ensure that you know all the values are not. So here you know the value of T1 is known to you, then T2 is not known because you are in need of T2, then T3, yes, you know the highest possible temperature, and T4 is not known to you. So use Pvt relation for 1 to 2 and 3 to 4. So from this you can easily find the value of that T2 and T4. So for Pvt relation I told you in the first class itself. So it is, if it is 1 to 2, P, then V and T. So 1 to 1 relation, that is P1 by P2, V2 by V1, T1 by T2. So whole power 1 by gamma and 1 by gamma minus 1. Okay, so you neglect this. So now it is P and T. So P1 by P2 or T2 by T1. So interchange the numerators and denominators. So P2 by P1 is equal to, that is nothing but the pressure ratio. So that is equal to T2 by T1. So you are in need of this T2 value. So you bring this 1 by gamma minus 1 to this side. So that will be gamma minus 1 by gamma. So this is nothing but the value of the pressure ratio that is given to you. Is it given in the pressure ratio? So you look at what is the pressure ratio, that is, yes, it is 5. The pressure ratio is 5. So you can see that. So you can find the value of the unknown, that is T1 is known to you. So you can find this RP is known to you. So the unknown T2 can be found out. Similarly, use 3 to 4. So that is the same Pvt relation. So T3 is known to us. The maximum temperature that is given to you. So T4 is equal to T3 divided by RP into gamma minus 1 by gamma. So that is RP power gamma minus 1 by gamma. So you can get the value. So 5 into this, what is that, RP? RP is 5 whole power 0.4 by 1.4. Okay, so you can get the value of this T4. So substitute in this turbine and this compressor equation. So you can get the value of the net work done. Since you know the value of power already and now the net work done is known to you, so you can easily find the value of MA. So all this has to be carried out within 2 or 3 steps because you don't have enough time. So that's why, so you should be thorough with this Pvt relation. So what are the things that are known or unknown, and how this gamma minus 1 by gamma comes. So everything should be known to you. So you have to carry out with various steps, and you should be thorough with all these changes. So the next is, a gas turbine plant operates on an as standard Breton cycle between the temperature limits. So the temperature limits are given to you, that is 27 degrees centigrade and 800 degrees centigrade. The pressure ratio at which the cycle efficiency approaches the Carnot cycle efficiency. So eta is known to, eta, the formula is known to you, 1 minus 1 by Rp whole power gamma minus 1 by gamma. So a hint is given to you, the pressure ratio at which the cycle efficiency approaches Carnot cycle. So since the higher and the lower temperature limits are given, so you first initially want to find the efficiency of the Carnot cycle. So if you find the efficiency of the Carnot cycle, so you can use here, so you have to find the pressure ratio. So you can find the value, that is for Carnot, eta for Carnot, 1 minus TL by TH. So that is temperature, lower temperature and higher temperature. So you can find the value of the Carnot that you substitute here, and the only unknown will be Rp. So that is the thing you have to answer. So that is efficiency of the Carnot is equal to 1 minus T minimum by T maximum, that is equal to 1 minus 300. So you get the efficiency of around 0.2. So this is the efficiency. So you have to use for this Breton cycle because the hint is given to you. So 1 minus 1 by Rp whole power gamma minus 1 by gamma. So you can write, so everything is known to you, everything is known, that is the efficiency is known to you. So the only unknown will be this. So bring back this to this side. So you can get the value of Rp. So the Rp value is given as 86.08. So that will be the pressure ratio for this given problem. So next is a Breton cycle working under a maximum power producing condition as a thermal efficiency of 49%. And the lowest temperature in the cycle is given as 350 Kelvin. And what is the maximum cycle temperature? So we know the diagram for this TS diagram for this Breton cycle, and we also know the efficiency. So eta is known to us, it is 0.49, and the lowest temperature in the cycle is given, T1 is given to you. So the formula that has to be used for this one is to find the maximum temperature is eta is 1 minus root of T minimum by T maximum. So the maximum temperature is the thing you have to find out, and this is known to you. So substitute the value. This is a direct formula. So directly you can substitute in the formula into the get the answer. T max is equal to 1345.6 Kelvin. So now, so you can see this problem, that is air enters the compressor of an ideal air standard Breton cycle at 100 kilopascal and 300 Kelvin. So it enters the compressor, that is P1, T1 are given to you, with a mass flow rate is given, m dot is given, or ma, whatever may be. So it is given to you, it is 1.5 kilogram per second. The compressor pressure ratio, that is P2 by P1 is given to you. P2 by P1 is 10, and the heat addition during the cycle is, so heat addition during the cycle is what is that, Q. Q is the heat addition, it is 1237.5 kilowatt. So for air, so assume the constant CV values, okay. The turbine inlet temperature, so what is the turbine inlet temperature? So turbine inlet temperature is nothing but a T3. We all know that is the maximum temperature. So where this turbine inlet, that is when you draw this TS diagram, you can see that, so 1, 2 and 3 and 4, this is the maximum temperature. So that is the turbine inlet. So this region indicates turbine, and here it is compressor. Right. So 3 to 4. So you have to know this T3 value. So for that, some conditions are given to you. So how can you find the value of T3? So some heat addition takes place. So during the cycle, so heat is added at some point. Heat is added. That is Q. Q is added. And similarly, so you can see that some what is that? The temperature of you know that addition temperature is T2, we don't know what is the value of T2, has to be determined, and T3. So this is the value of, so you have to find the value of this, the T3. So what? So this may be a combustion chamber. So this is a combustion chamber. Okay, so heat addition takes place. So the sum of these two will be equal to this. Right. So that means you are going for an equilibrium equation. So Q plus this T2 or whatever may be. If it is, if this is also Q, okay, you can see that it is MCP into T2, or this will be equal to MCP into T3, like that. Okay, so Q, everything is Q. So if it is Q1 and this is Q, so Q plus Q1 will be equal to this Q3. Right. So this is the diagram which represents for that given problem. Okay. So you can go to that problem. So that is, you can see here. So combustion chamber is given here. So that is Q is added into this combustion chamber with 1237.5 kilowatt, and some heat energy is added. So as I told you, Q, here this is also Q, MCP into del T, that is T, that is T2 plus Q dot will be equal to MACPA into T3. So from this equation you have the value of T3. So you should get the value of T3 only when you know the value of T2. So because Q is known to you, so MACPA, so you can you know the value of MA, you know the value of CPA. So you can easily find the value of the only unknown, that is T3. So how will you find T3? Only if you know T2. So for T2 you use the relation, Pvt relation, that is T2 divided by T1 is equal to the pressure ratios, that is P2 and P1. So the pressure ratio is given to you, it is 10, so 10 power 0.4 by 1.4. So that is equal to T2 is around 579.2 Kelvin. So the T2 can be substituted at this place. So if you see you look at this equation, so MACPA into T2 plus Q dot is equal to MACPA into T3, right? So this is also Q. Okay, so MACPA into T3. So now so divide the equation by MACPA. So this you will get the value of T3 at this side. So here T2 plus Q divided by MACPA. Okay, so MACPA. So you know T2 you know the value of T2, you know the value of Q that is given in the problem, and this is T2 is determined, and MA is known to you, and CPA is also known to you. So the only unknown will be is T3, so that can be found out. So that is the temperature before expansion, or the temperature at the inlet of the turbine is around 1400 Kelvin. So you can look at this choices, and you can see that it is 1400 Kelvin. So the answer is C. So next problem. So in a gas turbine working on Breton cycle, the product of combustion having Cp and Cv as 0.91 kilojoule per kilogram Kelvin, Cp and Cv are given to you, enters the turbine at 20 bar pressure. So the value of P3 is given. It is then expanded to 1 bar in turbine, then it is expanded to 1 bar. So that is P4. Find out the work done of the turbine if the maximum temperature, that is T3, is given to you. So you have to use the formulas which are so you have to use the formula where you have to get this value. So what is the question here? So you have to find the work done by the turbine if the maximum temperature is 1500 Kelvin. So the work done, so work done is mCp into del T. So this del T is T3 minus T4. So Cp is given to you. If it is for unit mass, then Cp into T3 minus T4. So the maximum temperature is given to you. It is 1500 Kelvin, and the pressure is also given to you. P2 is equal to P3. This is a PV diagram which represents this PV diagram. So that is 1, 2, 3 and 4. So the maximum P2 is equal to P3, it is 20 bar, and P1 is equal to P4 is equal to 1 bar. So if you have to find the work done by the turbine, that is H3 minus H4, we know that is Cp into T3 minus T4. Okay, so T3, the maximum temperature is known to you, and what is the value of T4? So use Pvt relation for 3 to 4. Okay, so from that, so you can see that T3 by T4 is equal to P3 by P4 whole power gamma minus 1 by gamma, which is equal to 20 divided by 1 whole power. So you can 1.3 minus 1 by 1.3 is equal to T4, which is 751.36 Kelvin. So T3 is known to you and T4 is known to you. The value of Cp is also known to you. So you substitute and you can easily find the value of the work done by the turbine. So that is the work done by the turbine. So what is the value? It is 680 something. Yes, it is 681.26. So the answer is C. Okay, so the next one is a simple gas turbine power plant operating on Breton cycle has the following specification. The maximum cycle temperature is given, so T3, and minimum cycle temperature is given T1, and maximum cycle pressure is given P2 or P3, when minimum is given to you. So you can find the what is that pressure ratio, that is P2 by P1. You can easily determine the value of this pressure ratio, and maximum temperature is given. So with the help of that you can find the unknown. So as I told you, so you can find the value of pressure ratio. So the unknown, you can find T2 can be found out with the help of pressure ratio, that is Pvt relation. And similarly for what is that T3 is known to you, maximum temperature, and T4 can be found out with this pressure ratio, with that Pv relation, and then this T4 is known to you. So now what is the question? That is the net work output. So that is Wt, the work done by the turbine minus the work done by the compressor, WT, WC. So if you subtract these two, so this is T3 minus T4 and this one is T2 minus T1. So if you find this, so if you subtract these two, that is T3 minus T4 minus of T2 minus T1. And if some specific heat is given to you into Cp, and you can find for unit mass, that is unit kg. So that is M is 1. So T3, T4, T2, T1, everything is known to you. So you can easily find the value. So that is around 250 kg. So the net power output of the plant in kilojoule per kilogram is 250 kg. Okay, next we can see the effect of regeneration. So what are the effects of regeneration? So regenerator effectiveness, so which is equal to, so the regenerative effectiveness is equal to, so actual temperature rise of air, so that actual temperature of rise of air is T5 minus T2 and maximum temperature of rise possible, so that is T4 minus T2. So it is the ratio between, so this actual temperature rise of the air and the maximum temperature of the rise possible. Okay, so I will show you a diagram which is related to this regenerator, that is TS diagram. Here Q1 and Q2, both of which decreases, whereas the net work that is obtained, it remains unchanged due to this regeneration. So the efficiency of the cycle, so that is W net by Q1 increases. So even though this Q1 and Q2 decreases, but the net work remains the same. So you see here, so eta is equal to W net divided by Q1. So even though this decreases, this Q1 decreases, so but this remains the same as it is. So when it remains the same, so the denominator is reduced further and further. So that means, so the value, so without change in this, even though there is no change in this network, the efficiency will increase. Okay, so the efficiency increases. So in practice, the regenerator is costly, heavy and bulky and causes pressure losses. So you can see, so what are the demerits of this regenerator is, it causes pressure losses, so which may bring out the decrease in the cycle efficiency. So so it has to be balanced. Okay, so this decrease in cycle efficiency and so will affect the performance. So you have to you have to balance this system. Okay. So this is the diagram which represents the effect of regeneration. So this is for what is that, compressor. So this is actual, this is ideal, and this WC is actual, and similarly here it is actual, WT, and here it is WT ideal. Okay. Now we can go to a question. So that is gas turbine cycle with regenerator, it improves. Now only we have seen with the regenerator, it improves the thermal efficiency of the cycle, right? So gas turbine cycle with regenerator, it improves the thermal efficiency of the cycle. You can see, so what is the function of the regenerator? So it is a heat exchanger which is installed on the gas turbine engine, through which the turbine exhaust gas passes. The compressed air is then heated in the exhaust gas heat exchanger before the flow enters the combustor. So using a well-designed regenerator, the thermal efficiency of the gas turbine engine can be increased. So when you use regenerator, so the thermal efficiency of the engine increases. So for the previous question, so the answer is thermal efficiency. The next one is efficiency of the gas turbine is increased by, so either reheating, cooling, so intercooling is not there, so this option will also be, so you have to find out this option also, maybe reheating and adding a regenerator. We know that, so efficiency increase with the help of regenerator. So this is the right answer. Okay. So adding a regenerator. So you can see here. So with intercooling, you can see the work done by the compressor is less, and the net work is less, but it also increases the heat supplied. So the net effect will decrease the efficiency. So as I told you, intercooling, so efficiency will not increase further. Okay, so then reheating increases the net work by increases the work done by the turbine, but it does not increases the efficiency. So reheating, so the net work increases. Okay, the net work increases, the net work by increases work done by the turbine. Okay, so then regenerator, if you go for regeneration, so installation of this heat exchanger in the gas turbine cycle, and when these heat exchangers are used, so it improves the efficiency. So you can notice the improvement in the efficiency. So that means adding this regenerator may improve the efficiency of the cycle. So the efficiency, regenerative efficiency may be improved. So the cycle efficiency may be improved when you add this regenerator for around 5%. So more than 5% is improved. So the answer will be, the answer for this question will be, so adding a regenerator. Adding a regenerator. The next is a regenerative gas turbine cycle is having a 100% efficient regenerator. Okay, it is an 100% efficient regenerator. Expansion and compression are ideal. Okay, the temperature at the end of the compression is, it is 500 Kelvin, and the peak is 1300 Kelvin. Pressure ratio is given to you. P2 by P1 is given. So at the end of the compression, T2 is given, then peak temperature T3 is given. Okay, if air is the medium, the amount of heat recovered due to a regenerator. So the amount of heat recovered, so you have to find the amount of heat recovered. So from this diagram, so regenerator is used. So as I told you, T2 is given to you, and what is that peak temperature? So I told you it is T3, right? It is T3. Okay. So when it is T3, when the regenerator is not used. So now the regenerator is used. So you look at this diagram, this TS diagram, you can see, so the regenerator, when it is used, so the temperature increases further, and now it is 4, and the regenerator temperature, and this, what is this, the temperature at the exit of the turbine, it remains the same. So you can see, because it is an 100% efficient regenerator, so the temperature after regenerator should be equal to the temperature at the exhaust from the turbine. This is a condition for this 100% efficient regenerator. Okay, so now, so instead of T3, you are going to substitute this as a T4. Okay, so T4 is given to you, it is 1300 Kelvin, and T2 is also given to you. So now use the Pvt relation for 4 to 5. So if you find the value of T5, so that will be equal to T3. Am I right? So because T3, that is the temperature after regeneration, should be equal to the temperature at the exhaust, temperature of the exhaust from the turbine. Okay, so you can see here. So T5 will be equal to T4 divided by P4 by P5 whole power gamma minus 1 by gamma. So P4 by P5. So that is nothing but the pressure ratio. So that is given to you. It is around 6. The pressure ratio that is given is 6. So P2 by P1 will be equal to P4 by P5. right? So that is 6 is given to you, it is 779, the value of T5 is given. So you have to find the value of heat gain due to regenerator. So what is the amount of heat gain due to this regenerator? So that is M. So if it is for Q for per kg, then this will be equal to CPA into this T3 minus T2. So now T3 is nothing but T5, then this is known to us minus T2. Okay, T2 is also given, so you can easily find the value. It is around 280.53. It is around 280.53. So that is given here. So it is 280. So the answer is C. So you can see that, so the exact decimals were also given. So that means you will get this answer. If the decimals are given to you, you will get the answers exactly as 280.53. So when you substitute in a appropriate way. Okay. The next one is, in a regenerative Rankine cycle with one open feed water heater, steam enters the turbine at 15 megapascal and it is condensed in the condenser at a pressure of 12 kilopascal. So here 30% of the steam leaves the turbine. So that means the remaining 70% is there, okay, at 2 megapascal and enters the open feed water heater. The specific enthalpy at the exit of OFWH is given there. So that is open feed water heater. So you enthalpy is assumed, and that what is that, at 2 megapascal it is 2798 kilojoule per kilogram, at 12 kilopascal it is 200 kilojoule per kilogram. So when you see this, you can say 30% of the steam leaves the turbine. So 30%. So H1, H2 and H3. So this is this leaves the turbine. So H3 will be equal to, so the sum of these two, that is H1 is 0.3 into H1 plus the remaining 0.7 into H2 will be equal to the value, that is H3. So the sum of this is the open feed water heater. If you add these two, you will get the value of H3. But an hint is given to you that only 30% of the steam it leaves the turbine. So that is H1 is 0.3 into H1 and H2 is 0.7 of that H2. So you will get the value of 979.4. So this is the specific enthalpy at the exit of this OFWH. It is so. If the problem is with the combustion chamber with open feed water heater, so that means so far we have seen some equilibrium equations were obtained. So you have to use that equations. So that means you have to maintain the system in equilibrium, and for that you have to write the equation. Based on that you have to arrive the unknown datas. The next is the effect of intercooling. So by staging the compression process with perfect intercooling, the cycle efficiency decreases. So where the small cycle without intercooling. So for minimum, so you can see the diagram, for minimum work of compression, the intercooler pressure, where P1 and P2 are suction and discharge pressures. So you can see here. So this is the diagram which represents intercooling process. So you can see these are all constant pressure lines. These are all constant pressure lines. So when you draw a diagram between temperature and entropy, so you will get like this. So 1 to 2 and 2 to 3 is, this is a intercooling process, and 3 to 4, then 4 to 5 and 5 to 6 and then to 1. And 1, 2. So this is the diagram which represents intercooling. So that is 2 to 3 represents the intercooling here. Okay. So it permits more heat recovery from the turbine exhaust gas, with the result that reheating along with regeneration may bring about an improvement in cycle efficiency. So the optimum reheat pressure for the maximum work is also given to you. Okay. So now, so we can see a problem. So air enters a multi-stage compressor 1 bar and 30 degrees centigrade and delivers at 200 bar. So determine the minimum number of stages required when the maximum discharge temperature is limited to 190 degrees centigrade and the polytrophic index is given as 1.3. So assume the perfect intercooling with the minimum work. So you have to find the minimum number of stages. So you have a formula for this. So that is overall pressure ratio is equal to pressure ratio between these stages. So overall pressure ratio. So what is the overall pressure ratio that is given? So you can see here the overall pressure ratio is P2 by P1, that is 200 by 1 is 200, and you have to find the pressure ratio between these stages. So what is the pressure ratio? So we know the Pvt relation, that is T2 by T1 is equal to P2 by P1 whole power gamma minus 1 by gamma. So you know the value for this. Okay, so you can find the pressure ratios. So you can see here, so that is around 190 degrees centigrade. So 190 degrees centigrade. So 190 plus 273, and the other one is 30 degrees centigrade. So you can see that 30 plus 273. So you can get the pressure ratio, that is P2 by P1, which is equal to 6.279. So 200 is equal to, the overall pressure ratio is 200, that is 200 divided by 1. So 200, which is equal to the pressure ratio between the stages, 6.279 whole power n. So you find the value of n, so that is 2.88 or otherwise 3. So the number of stages that is for this compressor is 3. Okay, so that is the minimum number of stages. The next is the effect of reheating. So by staging the heat supply process, okay, you can see that 1 to 2, 2 to 3, 3 to 4, and 4 to 5, and 5 to 6. So by staging the heat supply process with a combustor and a reheater, the cycle efficiency decreases. So you have to note down that, so when you go for reheating, the cycle efficiency decreases. Okay, so it is because the heat supply process within the combustor and the reheater, so the cycle efficiency. So when you go for staging the heat supply process with these two, that is combustor and the reheater, the efficiency of the cycle decreases. Okay, so next is, so calculate the efficiency for the same, that is of the open cycle gas turbine operating as shown in the figure is given to you, assuming the specific heat of the gas and the air are same and neglecting the increase in mass flow due to the fuel addition. So this is the diagram which is given to you. So calculate the efficiency of the open cycle gas turbine. So 1 to 2, so 1 to 2, 2 to 3 is the heat addition takes place, and similarly here also this is heat addition. Okay, and net work done by the turbine and the compressor is, so you have to, these are all the work done by the turbine, and this is the work done by the compressor, and here it is the amount of heat added, let this be Q1 and this be Q2. Okay, these are the amount of heat that is added to this diagram. Okay, so now, so what is the question? The question is efficiency, eta, that is output by input. So what is the output? So that is the work done by the turbine minus work done by the compressor, and the amount of heat energy that is added is the input, that is here it is Q1 and Q2. So if you add these two, you will get the value. Okay, so you go to the problem. So you can see here efficiency is net work by heat input. So as I told you, so the turbine work, these are all turbine work, T, these are all turbine work, and this is compressor work, and this is the amount of heat energy that is added. So Q1, then Q2, am I right? So Q1 and Q2. So when you substitute all this, so whether all these values are given, yes, you look at the diagram. So T3 is given to you, T4, T2, T1, all the temperature values are given to you. So simply you substitute all those, so you will get the value of efficiency. The value of efficiency is 0.644. The next question, calculate the efficiency of the given Breton cycle. So option is given to you. So this is the diagram. So the same formula you are going to apply for this. So eta, so that is what is the, this is Q, maybe Q1, maybe Q2. So T5 minus T4 and T3 minus T2 is the heat energy that is supplied, and here it is, you can see. So if you T3 minus T4 plus T5 minus T6 minus of T2 minus T1 will give you the net work done. So if you find the ratio between these two, you will get the value, am I right? If you get the ratio between these two, you will get the value of this efficiency, that is 48.86. The same. So T3 minus T4, T5 minus T6. So these are all turbine works, and this is compressor work, and this is the heat energy that is at Q1 and Q2. Okay, substitute all the values that is given, so you will get the value of efficiency is 48.86. So the answer is 48.86. Answer is B. Okay. And the next is in a reheat gas turbine cycle. So what happens? Mean temperature of the heat supply increases, mean temperature of the heat rejection decreases, then compressor work increases. So reheat gas turbine cycle. So the answer is regenerator can be installed to improve the efficiency, that is regenerator installation or the addition of the regenerator. So will be the right answer, though the answer is D. So the pressure ratio of a reciprocating compressor is 8 and having a clearance volume. So this is about compressors. So and next is in a gas turbine power plant. If a regenerator of 80% effectiveness is installed, then the thermal efficiency is what? So what is the thermal efficiency? Okay, eta thermal. So assume enthalpy at different points in the cycle. So H1 is given to you, H2 is given, H3 is given, then H4 is given. Okay, so regenerator effectiveness is given to you. So the formula for effectiveness has to be taken. And the formula for effectiveness, that is when you go to this diagram, you can see that it is A and B. So A and B you can see, so that is TA minus T2 divided by T4 minus T2, TA minus T2 by T4, that is HA minus H2 by H4 minus H2. So from this, so you find the value of the unknown, only unknown HA, that is HA is 798 kilojoule per kilogram. So now you can find the heat supplied. Heat supplied is H3 minus HA. So you can see that the amount of heat energy that is supplied, H3 minus HA. So it is 597 kilojoule. So the net work done is work done by the compressor and turbine and work done by the compressor. Difference between these two. So H3 minus H4 by H2 minus H1 will give you the net work done. So the amount of heat energy that is supplied. So for this, the amount of heat energy supplied for this 80% effectiveness of the turbine power plant, if a regenerator is added, so you can say that it is, the value is so 47.7%. So 285 is the net work done and 597 is the amount of heat energy that is supplied. So here the heat energy that is supplied should not be considered from 3 to 2. Okay, so here a point is there. So H3 minus HA is the amount of heat energy that is supplied for this with a regenerator with 80% effectiveness. And the next one is, an ideal Breton cycle has network output of 150 kilojoule per kilogram and a back work ratio is given to you, and this is not work ratio, it is a back work ratio, that is WC by WT. Okay, back work ratio. if both turbine and compressor isentropic efficiency becomes 85%. So eta C and eta T are 0.85. So the new net work output of the cycle would be, so what is the new net work output of the cycle? So the net work output, a new net work output has to be given. So when you look at this diagram, so now you have the efficiency is not 100%. So you have to go for two stages. So one is you have to find for this ideal and you have to find for this actual. Ideal and actual. So in case of ideal cycle, it is 1, 2, 3, 4. So the net work done will be, here it is Wt minus Wc. So the net work done is given. It is given as 150 kilojoule per kilogram. The net work output is given, it is 150 kilojoule. And the back work ratio is given, that is Wc and Wt. The ratio between the work done by the compressor and the turbine. It is given as 0.4. So Wc is 0.4 Wt. Okay, so we know that Wc minus or Wt minus Wc is equal to 150. So instead of this Wc, you can write as 0.4 Wt. So Wt minus is equal to 150, right? So this you can find the value of Wt. If you find the value of Wt, substitute in this equation, you can get the value of Wc. So Wt is 250 kilojoule per kilogram, and Wc is, you can find the value, it is 100 kilojoule per kilogram. Okay. So now, so the new cycle is given with a 0.85% or 0.85 or otherwise 85% for both the cases, for compressor as well as turbine. So in the previous case, you know that the work done by the turbine is 250 kilojoule and the work done by the compressor is 100 kilojoule per kilogram. So in the first case, so that is for 250 kilojoule per kilogram, so it is the efficiency that is 250 kilojoule per kilogram is given to you. So in the second case, there it works at 100% efficiency. Now it works at 85% efficiency. So you are in need of the new net work done. So this is your question. So Wt will be equal to 0.85 of Wt dash will be equal to 0.85 Wt. So you find the value of Wt dash. Similarly, Wc dash will be equal to this Wc by 0.85. So you get all this. So the net work will be the difference between these two, Wt dash minus Wc dash, which is equal to 94.85 kilojoule per kilogram. So the next one, in a gas turbine plant working on Breton cycle with lower and upper temperature limit being 289 Kelvin and 998 Kelvin. So the temperature limits, the lower and the upper temperature limits are given to you. The optimum pressure ratio. So you have to find the optimum pressure ratio. So the formula is known to us for optimum pressure ratio. So with respect to the temperature, so Rp optimum is T max by T minimum power gamma by 2 into gamma minus 1. So use this formula. So you know the value of T max and T minimum. So you can get the value of R optimum, which is 8.75. So the next one is, when a gas turbine is followed by a steam turbine for power generation, the cycle is known as, when a gas turbine is followed by a steam turbine for power generation, the cycle is known as combined cycle. It is known as combined cycle. You can see here, only in combined cycle, the efficiency of Breton cycle is improved by utilizing the waste heat in the turbine exhaust gas. So that is in combined cycle. So you can get the, when a gas turbine is followed by a steam turbine for power generation, then that cycle is called as a combined cycle. Okay. The next one, a gas turbine plant operates on Breton cycle between the temperature limits. So the temperature limits are given to you. that is T1 and T3, the maximum net work done. So the maximum net work done formula is there, so use that formula. So that is Cp into root of T max minus root of T minimum whole square. The maximum temperature and the minimum temperature are there, so Cp is known to you, W net max is, substitute this, so you will get the value of this maximum net work. So that is around 239.46 kilojoule per kilogram. Okay, next is a gas plant operates on a Breton cycle between the temperature limits of 300 Kelvin and 1100 Kelvin. The efficiency of the cycle is corresponding to the optimum pressure ratio. So the efficiency, you have to find the efficiency in terms of percentage. Okay, so efficiency is 1 minus T minimum by T maximum. So you know the formula, you know T minimum and T maximum, so substitute in this equation, so you will get the value of this efficiency, which is 47.77%. So when you are getting the pressure ratios, or when you are getting the maximum and minimum temperatures, so you should know that, so you should know the formulas which are related to all this, because you are going to find the unknown, so based on the formulas. So you have to be thorough with the formulas in this Breton cycle. Okay. Next one. So a gas turbine based on Breton cycle is operating with a pressure ratio that is between the optimum and the maximum pressure ratio. Which of the following is true? So you can see that the first one, net work output is half of the maximum. So we are not studied like this. So the net work output is less than the maximum net work output. Then the net work output is of maximum work net output. You can see here, so that is W is always less than that W max. So the maximum the net work out is always less than that maximum net work. Okay. So the maximum net work output in the Breton cycle is given as, so this is the formula for, now only we have seen this formula, so mCp into root of T max minus T minimum whole square. So you have seen the formula, so that is W net max is equal to Cp into root of T max minus T minimum whole square, that is, the answer is B. Okay, so you can, so formulas, so you have to be thorough with the formulas also. So the next one is pressure ratio in gas turbine at which work output will be maximum. So when it will be maximum, you can see here, so T max by T minimum, gamma minus 1. So this is not there, and this one is also not there. We know that. So gamma by 2 into gamma minus 1. So T max by T minimum, that is gamma by 2 into gamma minus 1. So this is the thing, that is RP. So for the maximum work output, RP max. So this is optimum, so power 1 by 2, that becomes gamma by 2 into gamma minus 1. So this so you can see here, so in Breton cycle, so the formulas are very important. So based on the formulas, so you are getting questions, that is the objective type questions. So you have to be thorough with these formulas. Okay, the pressure ratio for maximum output is given to you, right? So with this, so far we have seen that Breton cycle, so about regeneration, reheating and intercooling. So among all this, so we have come across more number of formulas. So how regeneration has to be carried out. So when regeneration is carried out, what happens in the cycle? When reheating has been carried out, what happens in the cycle? When intercooling is carried out, what happens to the work done? What happens to the efficiency? So everything has been studied by us, and questions which are related to the above, related to the same also has been gone through in this lecture. And moreover, once again I want to request the students that you have to be thorough with the basics. So what are the basics? that are related to this thermal sciences. So you can see here. So even from the first lecture, I told you that the Pvt relation is very important. So the same, even now, even in this lecture also, we are applying this Pvt relation. So you should be thorough with the Pvt relation, and the step-by-step process has to be known to you. So interchanging the numerators and denominators. If you interchange the numerator on one side, you have to numerator and denominator on one side. You have to interchange the same on the other side also. So that is the thing the students are doing mistakes. So you have to do the same. So let it take some more minute, no problem. But you have to work out in a correct manner so that you can easily get the marks. Okay, so because you have negative marks also, so when you go for around 10 to 15 questions, wrong questions, so you may lose more marks. So that may not leads you to enter through gate. So be thorough with all the formulas so that are related to thermal sciences, and you can work out the problems. So now we are going to see a problem. So on this air standard cycle, which is working on this Breton cycle. So here it operates between the maximum temperature and the minimum temperature limits. So they are given to you. So then the turbine and the compressor efficiencies are also given. So the optimum pressure ratio at which the maximum power is developed by. So the optimum pressure ratio formula is known to us. So for this efficiency, so that is given to you. That is RP, that is pressure ratio optimum is. So efficiency of the turbine and efficiency of the compressor into T max by T minimum whole power gamma by 2 into gamma minus 1. So substitute that. So then you know all the values. So efficiency of turbine, efficiency of compressor, then maximum temperature and minimum temperature are known to you. So you directly substitute in that. So you will get the value of this RP, that is pressure ratio, that is optimum pressure ratio. So the answer is 3.197. And the next question is, an ideal gas turbine which is working on a Breton cycle has minimum and maximum temperatures. So T minimum and T max are given to you, and the back work ratio is given here. So it is not work ratio, it is back work ratio. So what will be the temperature at the end of the compression stroke? So the temperature at the end of the compression stroke, so you can see that, so it is T2. So at the end of the compression stroke, so that is T2. So T1 is given to you, T3 is given, and the back work ratio, we know that it is WC by WT. So that is, you have to find the value of the work done by the compressor and the work done by the turbine. So that is WC by WT is 0.5. So when you substitute this T temperature relations, that is difference in temperatures, that is T2 minus T1. So this is compressor and this one is a turbine. So T2 minus T1 divided by T3 minus T4 is equal to 0.5. So from this you can see that, so you can simplify this equation further. So by taking this T1 out or multiplying and divide that equation by T1. So T2 divided by T1 minus 1 and T1 will be out. And similarly here if you take T4 out, T3 by T4 minus T1 into T4. So this is 0.56. So from this equation you can see that, so we know the value of T1 and we don't know the value of T2, and T3 is known to you. So the only thing is you have to find the value of T4 and T2. So if you find the value of T4 and T2, you can easily find the others. So from this you can see that use the Pvt relation for this Breton cycle. So that is T2 by T1 is Rp whole power gamma minus 1 by gamma, and similarly T3 by T4 is also Rp whole power gamma minus 1 by gamma. So T2 by T1 is equal to T3 by T4. So from this you can arrive an equation for this. So you can find the value for this T3 by T4 minus 1, and from this T1 by T4. So you simplify this equation and you can get a value for this T1 by T4, so which is equal to 0.56. So we know that T2 by T1 is equal to T3 by T4. So from this equation, so from this you can can write like this. So interchange the numerators and denominators. So on both the sides, T1 by T2 will be equal to T4 by T3. So from this you can write that T1 divided by T4 will be equal to T2 divided by T3. T2 divided by T3. So you know the value, that is T1 by T4 is 0.56. So T2 by T3, for T2 by T3 also you can substitute this T, that is 0.56. So T2 is equal to 0.56 into T3. So from this you can find the value of T2, so which is equal to 728 Kelvin. So you can see that the option is B, that is 728 Kelvin. So in this question, that is maximum and minimum temperatures are given, and then back work ratio is given. So the back work ratio is WC by WT. So and the value of T max, that is T max, and T minimum is given to you. So with this you are going to find the value of T2. So T minimum is T1 and this is T3. So from this, so with only by using the Pvt relation you can find the unknown, that is T2. So you have to be thorough with the derivations that involved in this Breton cycle. So otherwise it is very difficult for us to work out this problem. So you should know the equation for back work ratio, that is okay, but anyhow the Pvt relation is very, very important in this. So without that we may not able to proceed further, because we should know that. So you can see here, so that is in this equation you can see here that that is T2 by T1 and T3 by T4 are equal. So without that you may not able to arrive that T1 by T4. So you should be thorough with this equation, and then you can proceed further and you may get the answer. And the next one is a gas turbine power plant operates on the Breton cycle between the minimum and the maximum temperature. The ratio of optimum cycle efficiency of a Breton cycle to the efficiency of the Carnot. So eta Breton divided by eta Carnot, operating between the same two temperature limits. So this is the temperature limit for both the cases. So one is eta C is 1 minus, this is Carnot, 1 minus TL divided by TH, that is TL is the low temperature and TH is the higher temperature. So for this you have to apply that, and for Breton cycle 1 minus 1 by RP whole power gamma minus 1 by gamma, or otherwise, so you can even, if you know the maximum and minimum temperature, so or otherwise if you know the relation, so you may not use the same formulas as that is given here. So even for the pressure ratio, so you can go for the temperatures that are given to you, but anyhow it will take a longer time. So you go for the relations that are given with respect to efficiency based on the given data, that is 1 minus root of T minimum by T max. All this you know. So efficiency of Carnot is known to you, and similarly efficiency of Breton is also known to you. So our question is to find the ratio between this efficiency of Breton and efficiency of Carnot, that is 0.5 by 0.75, which is equal to 0.67. Okay. So the next one is a gas turbine is supplied with gas at 5 bar and 1000 Kelvin while being expanded adiabatically to 1 bar. The specific heat is given to you, that is at Cp and Cv are given. So what is the power developed in kilowatt per kilogram? So you should know the power that is developed. So power is developed in kilowatt per kilogram of gas per second. So the power developed has to be given here. So it is Cp, mCp into T3 minus T4 is the formula for this power developed. So if you know the value of T3 and T4, you can easily find the value of this power. So but when you go here, you can see that, so the Cp and Cv values are given. So the value of gamma has to be determined, that is Cp by Cv, and T4 by T3 is equal to P4 by P3 whole power gamma minus 1 by gamma. So you can find the value of this T4, that is 653 Kelvin. So you can easily find this T4 and substitute here, because the value of the value of this higher temperature is given to you. It is supplied, a gas turbine is supplied with gas at 5 bar and 1000 Kelvin. So the value of P3 and the T3 is given to you. So you substitute here, so you can easily get there is no need for this pressure here. You can see that P4 is given, that is 1 and divided by this 5, that is P3, and P4 is 1. So T4 is equal to 1000 into 1 by 5, 1.36 minus 1 by, so this is determined with the help of the Cp and Cv values. So you can easily find the value, and the value is power is 361.7 kilowatt. Okay. The next one is, so now in this problem, so that is in a gas turbine plant, so the compressor efficiency is 85% and the maximum cycle temperature is 875 degrees centigrade. The working fluid is air, that is Cp is equal to 1 kilojoule per kilogram Kelvin. So which enters the compressor at 1 bar and 27 degrees centigrade under an operating pressure ratio of the temperature of air leaving the compressor. So you have to find the value of that that is the temperature. So that is the temperature of the air leaving the compressor in degree centigrade. So you can see that in this diagram, so that is TS diagram 1, 2, 3, 4. So this is the work done by the compressor and work done by the turbine. Okay, so you can see that, so the compressor efficiency, it is given to you, it is around 0.85. So it will be like this, the 2 dash, and here it will be like this, 4 dash. So when you want to find this work or the efficiency for this compressor, you can see that, so the efficiency of the compressor can be given as, that is T2 minus T1 divided by T2 dash minus T1. So this is nothing but the actual temperature. This is the actual temperature change, and this one is the, sorry, so this is the ideal. T2 minus T1 is the ideal temperature change, and this is the actual temperature change, that is T2 dash minus T1 is the actual temperature change. So the inverse is that is for a turbine. Okay, so that will be actual by ideal. Okay, so you can see that will be actual by ideal. So you can see here T2 minus T1 and T2 dash minus T1. So from this, so you can see that the temperature of the air leaving the compressor, that is, you have to determine the value of T2, right? So if you know the efficiency of that is efficiency of the compressor, or if you want to find the value of T2 dash, okay, that is here, that is actually if the temperature that comes out of this compressor, so actual compressor, that is actual temperature of this compressor, so T2 dash, then T2, T1. So you have to know what are the data that are given to you. So you look at the data that are given to you, so you can see that T2 is equal to T1 into Rp whole power gamma minus 1 by gamma. So this relation is known to us, so you can easily substitute in this equation, that is T2 can easily be determined, and T1, whether it is given, yes, it is given to you, T1 is given to you, the unknown is T2 dash. So if you find the efficiency of the compressor is given to you already, the only unknown is T2 dash, so T2 dash has to be determined. Suppose if it is not given, the efficiency is 100%, so you have to directly, you can use the equations for that. So without this ideal, without that actual cycle. Okay, so directly you can go for the efficiency. So right, so efficiency is equal to T2 minus T1 divided by T2 dash minus T1, and if it is for turbine, you can see that, so it is the inverse, and when you draw the curve like this, so you can see that so 1, 2, then it is 2 dash, 3 to 4, 3 to 4 to 4 dash. Okay, so this is the diagram. This 1 to 2 dash will represent the efficiency. You can go for the efficiency of the compressor, and here it represents the efficiency of the turbine. If it is 1 to 2, so the efficiency is 100%. Okay, if it is 3 to 4, the efficiency is 100%. The turbine works on 100% efficiency. But when you go for the actual values, so it changes. So instead of the heat addition will be from the 3 to 2 dash only, T3 minus T2 dash only. Okay, heat addition. Okay, so similarly for here it is this also. So this is that is the what is that 4 to 1 is the heat rejection. So heat rejection also it changes in case of this actual cycle. Okay. So 0.8, then you substitute all this, so you can get the value of T2 dash. Okay, right. The next one. So a closed ideal Breton cycle operates between the temperature limits of 830 degrees centigrade while producing a power of 100 kilowatt. So the ideal Breton cycle, it operates between the temperature limits 830 degrees centigrade and the power is around 100 kilowatt. The cycle operates in such a manner such that there is no need for any regenerator. So regenerator is not required. The temperature of the working fluid at the exit of the compressor, so that is T2. So what is the value of T2? So heat generation is not required, so you can say that is regenerator is not required, so T2 will be equal to root of T1 T3. So T1 is equal to, we know the value of T1, so T1, that is 273 plus 800 will give you the value, on T3 you know the value, so T2 can be easily found out with the help of this simple relation. So T2 is equal to root of T1 T3. So in a gas turbine, the compressor absorbs 100 kilojoule of work while the turbine develops 300 kilojoule of work. So the compressor absorbs 100 kilojoule of work and the turbine develops 300 kilojoule of work, and the heat supplied is around 400 kilojoule. So in regeneration, 40% of the heat is used. So the heat supplied after the regeneration. So what is the amount of heat supplied after the regeneration? So the net work is how much of heat energy is supplied and how much of heat energy is rejected. So that is nothing but 300 minus 100 is 400 kilojoule. So QR should be known to you. So 300 minus 100, so that is equal to 400 minus this QR. Okay, so that is not minus 100. So 300 minus 100 is equal to 400 minus QR. So that is 400 minus QR is 200. So QR is equal to 200. Okay, so QR will be, so 200 is equal to 400 minus QR. Right, so QR will be equal to, so 400 minus 200. So you will get the value of QR as 200 kilojoule. So that is heat in the exhaust gas. 200 kilojoule is there. So the question is 40% of the heat in the exhaust gas is used. So for this 200 kilojoule, so 40% is used. So for this 40% is 2 4s are 80, then it is 80 kilojoule. It is 80 kilojoule. So 80 kilojoule is used in the regeneration. So what is the remaining supply? So the remaining supply will be 400 minus this 80 will be equal to 320 kilojoule. So that is the value of this. What is that? We have to supply around 320 kilojoule. So the heat supplied after the regeneration is, after the regeneration, so actually the heat supplied is 400 kilojoule. Okay, so you have to supply minus this 400 from that 80, that is 40%. Okay, after regeneration, that is 40% of heat that is used in this regeneration. So you have to subtract that 80. So 400 minus 80 is 320 kilojoule. So that is the answer. Okay. An ideal Breton cycle without regeneration has pressure ratio of 6. So air inlet to the compressor is 0.1 megapascal and 30 degrees centigrade. So the maximum temperature that can be attained in the cycle is around 900 degrees centigrade. So the compressor and the turbine efficiencies are given to you. So the actual efficiencies are given now. So I have drawn the diagram for ideal and actual efficiency, that is TS diagram for actual and the ideal efficiencies. So you have to use that diagram. So based on that you have to find the heat supplied per kilowatt of output obtained per kilowatt. So you have to find, so use this relation, so which I have drawn earlier. So the same I have drawn earlier, 1 to 2, 1 to 2 dash, and 3 to 4, and 3 to 4 dash. So this is ideal and actual. And similarly here it is ideal and here it is actual. Okay, so you can see that, so you the efficiency of the compressor, you can see that it is ideal by actual, and for the turbine it is actual by ideal. You can see from that you can find that using the Pvt relation you find the unknown and substitute in this equation and substitute the unknown values, and similarly for turbine 3 to 4 use Pvt relation, find the unknown and substitute in that equation. So you find you will get the value of the unknown, that is T4 dash, so which is equal to around this much. So the net work done, you know, that is Wt minus Wc, so which is equal to the Cp value. So Q is equal to mCp into this del T, that is T3 minus T2 dash. So that is the heat supplied. How much of heat energy is supplied? So from this 3 to 2 dash. Okay, it is not 2, so 3 to 2 dash. So if you find the change in temperature between 3 and 2 dash, you will get the value of this heat that is supplied per kilowatt of output that is obtained. Okay, so you can see from this diagram itself, you can see that this is an this is for ideal part of the compressor, and this is for actual part, and similarly the ideal part for turbine and actual part. So this is the this is for the heat that is supplied, and this is for the heat that is rejected. Okay, so this is for the heat that is rejected. So heat rejection is more, so that heat supplied is there, it is less. So you can find the value, so that is heat supplied per kilowatt, the work obtained is 648.78 divided by 223.17 kilojoule, that is equal to 2.9 is the amount of heat energy that is supplied. Okay, the next one is, so the Brayton cycle is a theoretical cycle for which turbine and it is similar to which cycle. So you can see that, so during this compression as well as the heat addition, so whether this Brayton cycle is similar to that of the diesel cycle, that is Brayton cycle is a theoretical cycle for which the turbine and it is similar to which cycle. So the option is, so you can see that a constant diesel cycle, so you can see that the pressure addition takes place at a constant pressure. So similarly it is here also the pressure addition, heat addition takes place at a constant pressure. So from the first itself you found the answer, so you can tick this and the answer is A. Okay, so all these options, so Otto cycle, constant volume. Okay, so here you have diesel cycle in compression and it is Kaplan gas turbine, so this is not there. Okay, so then Atkinson cycle and impulse gas, so this is also not there. Okay, so the correct answer is A. Okay. So next one is, so the Brayton, so you can see here a closed cycle gas turbine plant operating on a Brayton cycle between 300 Kelvin and 1100 Kelvin. So some more data pertaining to the cycle are given below, that is the pressure ratio of the cycle is given, compressor efficiency is given, then calorific value is given, then combustion loss is given, Cp value and gamma value is given. So now you have to find the air fuel ratio of the plant. So you can see that the air fuel ratio, that is, so eta C, so as I told you earlier, so you have to use the same diagram and you have to use the same relations. So that is the efficiency of compressor is T2 minus T1 divided by T2 dash minus T1. So you know the value of T2, so find the unknown, that is T2 dash. So the heat that is supplied here is Qs is equal to Cp into T3 minus T2 dash. T3 minus T2 does. So from that, so you know the value of the amount Q, that is heat supplied, as 10% of the heating value is lost. So what is the efficiency? So you can see here 10% of the heating value, that is the combustion loss. So 10% of the heating value is lost here. So the efficiency of the heat is 90%. So each kg of the fuel will contribute around 0.9 into this calorific value is, what is the calorific value? It is 41,800 kilojoule per kilogram. So it is 0.9 into 41,800, you will get the value. So 37620 divided by this 584, you will get the value of this air fuel ratio, that is 64.4. Okay, so you will get the value. So the next is, so in a Breton thermodynamic cycle, so that is shown in that diagram. So a compressor, turbine, so you all know this. So work done on the turbine is same as work done by the compressor, because, so what is the reason? What is the reason for this? So it is in TS diagram of a Breton and thermodynamic cycle, so which is working on the turbine same as that of the work done by the compressor, because turbine and compressor are on the same shaft, which results in similar temperature change. So you can see that, so turbine and compressor lies on the same shaft in the cycle. Okay, so this is the explanation. So you can see here, so the diagram will be like this, am I right? So when it is a compressor, a combustion chamber and a turbine, right or not? Okay, is this right? A compressor, a compressor, yeah, turbine. So can you identify the difference? So you can see here, so this is a compressor, so air is compressed. Okay, this symbol for compressor, and this is the symbol for combustion chamber, and here expansion takes place. So the expansion takes place. So turbine. So you can see that this compressor and the turbine, so it lies on the same shaft in the cycle. Okay, so that is why in Breton thermodynamic cycle, with this TS diagram, work done on the turbine is same as the work done by the compressor. Okay, so this is the reason for it. So the next one is, so you can see here in this TS diagram of reverse Breton cycle as shown, the expression for efficiency is given to you. So the expression for efficiency, so that is you can see that COP here, what is the amount of heat energy that is rejected, that is amount of heat that is extracted divided by this work, what is the work done. Okay, so you can go here. So what is the amount of heat that is extracted in this? So 1 to 2, so that is from 4 to 1. So that is from 1 to 4, the amount of heat energy is extracted. So in all the cases you can see T1 and this is T1 plus T4. So this is wrong. Okay, so you have the option on A, B, C. Okay, but you should know what is this one. Right, so if you find that change in temperature at these two regions, that is at if it is that is 1 to 2 and 3 to 4, so you can find that whether it is T1 minus T2 minus T1 minus of T3 minus T4. Am I right? If it is T2 minus T1, so plus T3 minus T4 or minus of, so if you subtract from this T2 minus T1 and T3 minus T4, so what you will get? T2 minus T1 minus T3 plus T4. Right. So now you can see that, so you have to look at the choices T2 minus T1 minus T3 plus T4. Others are plus, so you will not get this one. So this is also wrong. Okay, so you look at this minus T3 minus T4 should be there, this is also wrong. So the option is A. You can look at the option, so the option is A. Okay, the next one is So for a gas turbine working on Brayton cycle, if T1 is the temperature at the inlet of the compressor and T4 is the exit temperature of the turbine, then what is the work ratio? So you should find the work ratio. Here you have different options. So you have to change T1 by T4. So you have to get this T1 by T4 either in terms of temperature 2 or 3 or 1 and 4 is known to you. Now you have to find this with the relation T2 and T3. So then only you can able to find this work ratio. You can see here. So this is equal to W net, that is work ratio is W net by WT. Okay, back work ratio is different, WC by WT. Okay, this is work ratio. It is the net work done by the turbine work. You know, net work done, the difference between turbine and the compressor. So 1 minus WC by WT. So here the same you can write as 1 minus Cp into, for this efficiency, 1 minus Cp into T2 minus T1 by T3 minus T4 when you write in terms of temperature. Okay, so 1 minus T1, so you take T1 out, T2 by T1 will be there minus 1, and similarly T4 out, so this you will get this value. And in case of ideal Breton cycle, we know that T2 by T1 is equal to Rp power gamma minus 1 by gamma, and T3 by T4 is equal to Rp power gamma minus 1 by gamma. So you can equate these two. Okay, T2 by T1 is equal to the Rp power gamma minus 1 by gamma. Similarly, this one T3 by T4. So when you equate these two, you can see here, so T2 by T1 is equal to T3 by T4. So these two are similar to each other. Am I right? Okay, so you can cancel these two, T2 by T1 and T3 by T4. So you will get 1 minus T1 by 1 minus T1 by T4. So this work ratio is 1 minus T1 by T4. So it is here and you can find the answer. The answer is A. Right? On the next one. So you can see a gas turbine plant operates on the regeneration Breton cycle between, so minimum and maximum temperatures are given to you. The pressure ratio is given, it is 6. So what will be the efficiency of the regeneration cycle? So you know the formula, that is eta is equal to 1 minus T minimum by T maximum into Rp whole power gamma minus 1 by gamma. So this is already known to us. So 310 divided by 1075. So you directly substitute in this, you will get the answer. So that is 0.52. The answer is C. Okay, so these are all direct questions. So directly you have to substitute the formula or you have to use the formula according to the data. Okay, so next one is, so you can see here. So a gas turbine plant operates on the Breton cycle between the temperature limits, the maximum work done per kg of air and the corresponding efficiency. What is the maximum work done and the corresponding efficiency? So you know the value for, you know the ratio, that is ratio of temperatures, root of T minimum by T maximum. So you have to use that where you are going to use this maximum work formula, you have to relate with this minimum and maximum temperature with this maximum work done. Okay, so when you go here, you can see that the maximum work done is Cp into root of T max minus root of T minimum. So when you use this formula, you will get the value of the maximum work done. Okay, and when you use this efficiency 1 minus root of T minimum by T maximum, so you will get the value of efficiency. It is 239 and 47.2. 47.2 and 239. Okay, so you can see that it which is the nearest efficiency. So 47 and 239.9. So the answer is D. Okay, so the next one is, so you can see that in this problem, a gas turbine hot combustion products enter the turbine at 18 bar for 1400 Kelvin and exit at 1 bar. The isentropic efficiency is of the turbine is given to you. It is 0.96. So immediately you have to think of the diagram which represents the actual efficiencies. Okay, so ratio of the specific heat is given to you, that is 1.3, and CV is given to you. What is the work developed by the turbine? So the work developed by the turbine, so that is equal to, so you can see here, so that is 1000, what is that, you have to find the value of this turbine efficiency. So here you can see that T3 and T4 dash and T4. So the data that are given here are related with the turbine. Okay, so you know that efficiency of the turbine, formula for efficiency of the turbine, when actual efficiency is given, so you have to know, so how you have to write. So there you wrote us, here you wrote us T2 minus T1 by T2 dash minus T1. So that is ideal by actual. So now you have to go for actual by ideal. So that is T3 minus T4 dash by T3 minus T4. So you have to look at the given data, whether you know the value of T3, T4 and T4 dash. So you can, if you don't know the value of 3 and 4, 3 or 4, so if you know any one of the value, use Pvt relation for this isentropic process and find the unknown. Then you determine the only unknown in this turbine efficiency equation. So you determine that, so you will get the value of the unknown, that is T4 dash. You know that Cp by Cv is gamma. Then you find the value, the turbine work here is Cp into T3 minus T4. So now you know all the values. So you can easily write the answer is around 654. So it is, the answer is B, it is around 654.2. So like this you have to, so suppose if the efficiencies are given for compressor and turbine, immediately you have to know, so for compressor what is the efficiency, for turbine what is the efficiency when it is compared with ideal and actual. Okay, so you have to compare it with ideal and actual. So the next is, the efficiency of a simple gas turbine can be improved by using a regenerator, because, so what is the reason for this? Because the work, so when you go for that, so you can see that the heat required to be supplied is reduced. So that is the reason. So these are all direct questions. So there is no need for any explanation, because you have to study the theoretical part or the principles that are behind this regenerator and reheater. So all these were given to you already. Okay, so when you know the principles behind what is the use of regenerator, what is the use of reheater, so you can easily find the answer. Here you can see that, so can be improved by using a regenerator, because the heat required to be supplied, the amount of heat energy that is required to be supplied is reduced. So because when you are using a regenerator, so the temperature will automatically it increases. So there is no need to go for that is a higher heat energy, so to be supplied to the inlet. Okay, so when you use a regenerator, automatically the heat required to be supplied will be reduced. Okay, the next one is, so Breton cycle with infinite intercooling and reheating stages, which with approximate it will approximate. So what is the cycle? So it is Ericsson cycle. Am I right? Yes, it is Ericsson cycle. So with the introduction of this multi-stage compression with intercooling and multi-stage expansion with reheating, so TS diagram, it can be seen that the approach is made towards this isothermal process. So the cycle will be called as Ericsson cycle. So the answer is B. So these are all, so based on that PV and TS diagram, so you have to decide. So which is, so that only I am telling you, so you compare the cycles. Okay, you compare the efficiencies, you compare the cycles, PV, TS diagrams. So based on that you may arrive a conclusion, so how each and every cycles are related together. Okay, suppose if one is a constant pressure process, you have to see where the constant pressure process arrive in the other cycle. Okay, so in this Breton cycle, so we have seen about regeneration, then reheating. So we have seen the principles behind regeneration and reheating, then how when the efficiencies are given, that is when the actual efficiencies are given to you, how you have to react for the efficiency of the compressor and the efficiency of the turbine. And similarly, so we have seen a lot of problems which are related to regeneration, then reheating, and what are the uses of it. So the statements related to regeneration and reheating. So in case of this gate question, so you can see that at least one of the question may be from the statements, either from the statement of this regeneration and reheating, or the problems which are related to the efficiencies of compressor and the turbine. Suppose if efficiencies are given to you, so I told you, so how you have to use the equation. Okay, so with this, so the Brayton cycle, it comes to an end. So be thorough with the concepts which are behind this Brayton cycle, so you can easily work out the problem. So I think only few formulas are there, and the remaining things are based on this Pvt relation and efficiency equation. Thank you.